All right, folks, today's lesson is going to concentrate mostly on independent events versus dependents, but we are going to do some review of complements and some other items we've seen in this chapter. Okay, so starting out, we're going to talk about the definition of independent events. Okay, in general, when we think about events being independent, we're saying, suppose some event happens. That event happening would not affect the probability of the second event. It wouldn't make it more likely. It wouldn't make it less likely. Okay? Mathematically, what that looks like is the probability of A times the probability is equal to the probability of the intersection. So we're going to use an example that we can see from the setup that they're independent and then show how the math actually falls out to see that theorem happen. So here we go. The first one says we have a fair spinner over here. It's got 6 parts. They're all the same size. That's what makes it fair. Okay, we want to spin it twice, and our events are the first spin stops on an even number, the second spin stops on a multiple of 3. So because we're looking at spinning this thing twice, our sample space would look like 1, 1, 1, 2, 1, 3, all the way to 6. Then 2 with 1, 2 with 2, 2 to 6, all the way down. Our outcomes would have 6 for the first times 6 for the second. When you combine all those, there are 36 total. And with that, if we concentrate on our events, I said this would be pretty clear that they are independent. If we look at the first one, stopping on an even number, we'd be on 2, on 4, or 6. My second spin, being a multiple of 3, doesn't care what the first spin looked like. Because they're 2 separate spins, they would be considered independent. We're going to show that using this math. So to start out, we're going to find the probability of A. It says the first spin stops on an even number. I highlighted those over here. You don't necessarily have to, but those are 3 out of 6, which gives us 1/2. But I also want to talk about how we could get that same 1/2 using actually our sample space with the 2 spins. And this is going to be helpful for building up problems that are more challenging, not as obvious, and especially dealing with the intersection. So go ahead and write this down with me. What we're going to think about is our sample space in terms of a stem and leaf plot. Here's how it works. So go ahead and write event A and draw yourself this bar. And the stems go over here. That's going to be our first spin. So on the first spin, we could get a 1, a 2, a 3, a 4, a 5, or a 6. And then the leaves on this stem and leaf plot is going to represent the second spin. So I could get a 1 with a 1, a 2, a 3, 4, 5, 6. But this is event A, so we're only going to write the ones that work. So event A says the first one stops on an even number, meaning nothing with 1 would work. But with 2, I could have any number because the first spin has to be even. It didn't say anything about the second one. So 1, 2, 3, 4, 5, 6. Same thing, 3 doesn't work. 4, 1, 2, 3, 4, 5, 6. All of those would work. Nothing with 5. And then 1, 2, 3, 4, 5, 6. These leaves represent 2 with 1, 2 with 2, 2 with 3, and so on. So if we count up the leaves, there ends up being 6, 12, 18, and 18 over 36 gives you that same 1/2. And this is actually better for when we go to talk about this last part. Okay, so it's a little bit messier. You can definitely get the probability just thinking about the first spin, but this may help us with this. Okay, we're going to do the same process for B, just to help ourselves out for practice. Okay, it says the second spin stops on a multiple of 3. We know that 3 and 6 are 2 out of 6, and my probability is going to be 1 over 3. Okay, but I want to show you the stem and leaf way. So again, 1, 2, 3, 4, 5, 6, and we're going to fill out what works. So the second spin has to be a multiple of 3. So the first spin could be a 1 as long as it goes with 3 or 6. The second one, same thing. As long as it goes with 3 or 6, it's going to work. And then we're going to go ahead and just fill out the rest with that same pattern. And if we count those, 2, 4, 6, 8, 10, 12, 12 over 36 is also 1/3. Okay? But when we look at the intersection, this version is going to help us figure out the answer a little bit more quickly and more straightforward if we have them listed out. This says we want to look where A and B overlap. When we can see A and B clearly, we can see the overlap clearly. Okay, so I've got nothing with 1, which means those don't matter. But in 2, I want to look for 3 and 6, and those show up. Same thing with the next one. Okay, 3 and 6 show up on the 4s. And 3 and 6 are showing up there. Okay, you could do the same thing over here if you prefer. If we just look for the ones that have the 2 to start with, or the 4 to start with, or the 6 to start with. Okay, still circling, there are 1, 2, 3, 4, 5, 6 different outcomes that work over 36, which is 1/6. Okay, if you like this, okay, that may be helpful. You could also, if you want to just think first is even, I know it's going to be 2, 4, 6, second has to be a multiple of 3, so 2, 3, 2, 6, 4, 3, 4, 6, and 6, 3, 6, 6. You can list them out that way as a set to count them as well. It's entirely up to you. Here's what we're going to do, though, to show or mathematically prove that this is happening. Our definition says the probability of A times the probability of B should be equal to the intersection's probability. And so we're going to take our 1/2 and multiply it by our 1/3 and compare it to the 1/6. If they are equal, then our events are independent. If they are not equal, then our events are dependent. So 1/6 for this one is equal to our 1/6. That's our proof to show they're independent like we thought they were going to be. Alright, checking out the next one here. Should go a little bit quicker now that we know what the idea is. Says we've got the spinner from problem 1 again, and the first one is an even number, the second one has a sum of both spins greater than 8. Okay, so again we're going to have our 36 outcomes, and we're looking for the probability of A, probability of B, probability of the intersection, so that we can fill out that proof statement. So starting out, first spin stops on an even number. If you like to set it up this way, 1, 2, 3, 4, 5, 6. First being on an even number is here, here, and here, with anything from our second one. So there are 6, 12, 18 again. 18 over 36 gives us our 1/2. Okay, from the first spin, half of them are even. Okay, B. The sum of both spins is greater than 8, so 1, 2, 3, 4, 5, 6 again. And we want to put this with a number greater than 8. So if we're thinking about our spinner, our lowest sum possible, 1 with 1, is the sum of 2. And our highest sum possible is a 6 with a 6, and that goes with 12. We're only going to focus on the ones greater than 8, so that would look like 9, 10, 11, or 12. So we're going to go through these in order and decide, can we put a number 1 through 6 with our first number to get one of these sums? Okay, so 1, since my highest number is 6, is not possible. Okay, 2, again, highest number is 6, I only get a sum of 8, not possible. But as soon as we get to 3, we get a sum of 9 to show up. 4, I can do with 5 or 6, get a sum of 9 or 10. And then 5 could go with 4, 5 or 6 to get a sum of 9, 10, or 11. And then 3, 4, 5, and 6 for the last one to get 9, 10, 11, and 12. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 for this one out of 36, so 5 over 18. And now I'm going to go look for the overlap. So you can pick either of these steps or these sets to start with. It does not matter. But whatever set you're looking for, you're trying to find where B also happens or where A also happens. Okay, so if I'm looking at A, all of my even ones, I would just see where a sum greater than 8 is also happening. So the 4, 5, the 4, 6, over here, the 6, 3, 4, 5, and 6, those are the ones that are showing up. Okay, over here, just the ones with the even starting number, so those 2 and those 4. Okay, so total of 6 out of 36, which is our 1 over 6. So we can say that the probability of A times the probability of B when events are independent equals the intersection. It's probability. Let's check out for ours. 1/2 times 5 over 18. We want to compare that to 1 over 6. This on top is 5 over, then on the bottom 36. Doesn't reduce. That is not equal to 1/6. So these are dependent events. Let's go talk about y in terms of our original. It says the first one has to spin an even number. Y'all, as soon as you spin an even number, 3 is gone, 1 is gone, 5 is gone, that changes the probability of B happening. It's less likely. So these are dependent. It doesn't have to be less likely. It doesn't have to be more likely. It just has to change the probability. Okay? Alright, looking at this next one, it's imagine a fair coin is tossed 4 times. You want to find A getting all heads, B getting all tails, and decide whether they're independent or dependent, just like before. Okay, so different situation here. Fair coin only has 2 options, and I'm repeating this 4 times. So 2 for the first, 2 for the second, 2 for the third, 2 for the fourth. 2 to the fourth is 16 outcomes for this one. I want you to pause the video and see if you can come up with what A looks like, with what B looks like, so that you can find the probability of A and B. Make sure they get over 16. Okay, so pause the video and try that one for me. A is just heads, 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 heads. There's only one of them, over 16. B is tails, 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 tails. There's only one of them. And we're looking where A, the heads, 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 and B, tails, 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 overlap. Y'all, they don't. So the probability of not overlapping at all is 0. So when we go do our test, I hope you can see that these are going to be dependent because that was 0. But let's go ahead and check it out. Probability of A was 1 over 16, and we're multiplying that by 1 over 16 and comparing it to the intersection. And because this one is 0, it's obviously not equal, okay, but 1 over 256 is not going to work for us. So we put a therefore dependent. Okay, let's chat about y. Getting all heads, y'all, once you get heads, 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 changes this probability, because once you get all heads, it is impossible to get all tails, making it dependent. The probability was changed. Okay, this one says A and B. That's supposed to be C and D. So I'll fix those. And what I want you to do is see if you can complete this one from the beginning all the way through. Pause the video, take care for me. Alright, here are our sets. If we want a sum of 7, 1 with 6, 2 with 5, and so on, there are 6 out of 36, so probability is 1/6. When we talk about the first die being a 5, 5 could go with any number. So there are 6 of those. If you want to think about just the first die, 1 out of the 6 sides is the number 5, so you can think about it that way as well. Either way, we're going to think about the overlap. From the sum, only one of them had a 5 for the first one, or of these 5 starting numbers, only one of them had a sum of 7. Okay, so that is 1 out of 36. And our last step, we're looking at 1/6 times 1/6 compared to 1 over 36. 1 over 36 is equal. And with that, we can say these are independent events. Okay, because you can get a sum of 7 starting with any number. There was exactly one way to do it on that. Or similarly, if you're talking about starting with the number 5, that doesn't make you any less likely to get a sum of 7 because it is possible with each digit. Okay? So if you have questions when you're working on your homework for those independent problems, come see me. But the rest of the time here, we're going to review some of the other stuff we talked about this chapter. So we're going to go to complements first. We've done a little bit with complements, but we're going to talk about describing complements in words. So in order to do that, we're going to go talk about what everything except for looks like with all these symbols. So everything except for equals is not equals. Everything except for greater than is less than, but also equal. Similarly, the next one then would have to be greater than or equal. Greater than or equal here has the equal, so we just want the less than. Complement of less than or equal to is greater, and the complement of the word and is or. So we're going to use that on number 6 to describe what the complement would be by switching all of the symbols and words we see to their complement to write it out. Okay, so it starts out saying A is the event consisting of all ordered pairs x, y. So if we're describing the set, it looks like ordered pairs, and then they give us some requirements. We're going to, when we describe the complement, start out with the basis. Okay, so A complement, use the hat, is all ordered pairs x, y, that's given, and then for our requirements you go switch them. So it says where x greater than 0, so the complement of that would be where x is less than or equal to 0. This is a word that folks usually skip over, okay, but we talked about and having the complement of or. You do have to switch that to or. It's italicized to kind of remind you that. And then y equal 1, the complement would be y not equal to 1. And that's it. Okay, so it's all those ordered pairs. X is less than or equal to 0, or we've got the y value not equal to 1. Alright, couple probability here. The first one deals with complements in a way. Okay, so it says find the probability of rolling at least a 2 when one die is rolled. When we're talking about one die, the sides are 1 through 6, so at least a 2 would be 2, 3, 4, 5, 6. That's 5 outcomes over 6. But why this kind of deals with complements is I want to point out that this way, while straightforward, is not necessarily the best method for larger sets. So when we're talking about at least a 2, the only thing that's left out is the number 1. So this really says everything but 1. So I could say I know there's 6 total, take off the number 1, there are 5 left, and it's 5 out of 6, and that's a little bit faster. So I'm going to give you an example of a problem that convinces you this might be helpful with complements. If I wanted to find the probability of not perfect squares, and I'm looking at the numbers 1 through 100, I could go list out, well, 2's not a perfect square, 3's not a perfect square, 5's not a perfect square and go it that way, but it's faster to think about the ones that are perfect squares and subtract them from 100. Okay, so let's do it. If we think about our perfect squares, we've got 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, and hopefully with this pattern you know we're going to go all the way to 10 squared, meaning there are 10 perfect squares from 1 to 100. And that means there are 90 that aren't perfect squares. And then we've got 9 over 10 for our final answer, way faster than actually listing out the 90. Okay, so use complements to help you if you've got really large sets. Next one, it says find the probability of getting a sum of 7 or a sum of 8 when you roll 2 dice. Pause the video, try that one for me. On this one, you could do a set or a stem and leaf plot for each of these separately, but I'm going to actually encourage that you put them together because ORs for us is a union, and sometimes ORs, when you do them separately, you don't see that overlaps are possible, and we don't want to overlap things twice. When we're just listing them out in one set, we're not going to repeat ourselves. We make a point not to. Okay, so for these, it didn't have overlap, but sometimes they do. Just use one stem and leaf plot. So we're looking for a sum of 7 or 8. I know I can put a 6 here, but there's nothing bigger on a die to go with a sum of 8. The next one, 2 could go with a 5 to get 7, or it could go with the 6 to get 8. And then we're going to continue that through here. So we could have 4 or 5, then we could have 3 or 4, 2 or 3, 1 or 2, and there's 11 total out of our 36 when we roll 2 dice. Next up, are going to review a little bit with Venn diagrams again. I'll do this first one with you. So it says, suppose at HHS, 80% of the students carry a backpack or a wallet. 40% carry a backpack, 50% carry a wallet. If a student is selected at random, we want to find the probability that a student carries both a backpack and a wallet. Okay, I know that when I look at this 80%, that's my total. And it is possible for a student to carry both a backpack and a wallet, and in fact that's what we're trying to find. So the bubbles should overlap when we draw our Venn diagram. Okay, so go ahead and draw them with backpack and wallet titled, and then we'll go fill some stuff in. This 80% is talking about OR, which means it's our total. So when I take all of these pieces and put them together, it gets 80% of the population at Hays High School. And that just means there's leftovers here that don't carry either. Okay, but our job is to figure out where the rest of the stuff goes so we can answer this question. Okay, first it says 40% carry a backpack, so 40% would be here. Okay, remember, when I say backpack, I mean the whole circle, not just only a backpack. Right? Well, hopefully that clearly tells you already, without doing anything else, if 40% of the bubble is here, that would mean 40% would be in the only wallet section. Because I knew they had to add to 80. Okay, now I'm going to keep reading. It says 50% carry a wallet. We put 40 of it here. The other 10% would have to go here to get to our 50. And then if we go ahead and finish here, 40% was there, 10% in the middle, 30 here. And our question was asking, what was the probability that a student carries both a backpack and a wallet? Both is in the middle. That's our 10%. So we're going to put our final answer in a box. Okay, I want to show you another way to do this, though, and this is related to your note card. Okay, so on your note card, over here, it tells you that we can find the probability of the union by taking the probability of A plus the probability of B minus the intersections probability. So if I go back over here, just minimize this, and look at the pieces I have, I was told that the union was 80%. And that's supposed to be equal the probability of the first one, 40%, plus the probability of the second one, 50%. Okay, I'm going to pause for a second to take a look at this. The reason we had this equaling 80 and this middle actually equaling 10 is based on this relationship right here. If you take 40% plus 50, looking at our circles, we're counting something more than once. Okay? And at this point, you don't know what. We hadn't gotten that 10 yet. But that's the part of the intersection. You have to subtract off something to make those actually equal to take care of what's repeated. So when I'm looking at this, the 40% plus the 50% gives me 90, and I'm saying that that goes over 80% by 10. Okay, so that's another way to get the 10% without using the picture in the way that we used it. All right, so formula's got your back if you're ever stuck. Okay, but what I want you to do right now is pause the video and see if you can take care of this one with the swimmers and the wrestlers. All right, I actually like to start this one with the both. So 55% of people can both swim and whistle, and with that, I fill in the rest. I knew 80% could swim, so my total has to be 80, but 55% of it is already there, so there's 25% remaining. Same thing with the whistlers. 55% of the 70 go there, so there's 15% left over who only whistle, can't swim. With that in mind, we can answer these questions really quickly. Swim or whistle is our union, and that's 95%. You can get that by adding those up, or you can do it by taking those two and subtracting that off using the formula from your note card. Okay? Two separate ones subtracting off the intersection. Only whistle from your picture is 15%. And cannot swim or whistle is the complement of this thing up here. There's 5% of people left over in the box here, and that goes for our final answer. Next problem is a little bit of thinking and dealing with kind of some misconceptions about probability that I see. It says Jill computes the probability that she gets heads at least once in 2 flips of a fair coin. And so here's the setup. She looked at the probability of heads on the first or heads on the second, because that's what at least one means, one or both. Okay, then split them up and found their probabilities. Because it's an or, she added. And based on that math or adding, that's okay. We want to know, do we agree with the final answer being 1? Okay, if so, we'll defend it and show mathematically why. If not, we'll give the actual probability. So looking through here, let's start with our sample space. When we talk about flipping a coin, we could get heads, heads, if we're flipping it twice. We could get heads, tails. We could get tails, heads, or tails, tails. I like to list and count, so if we're just looking at our sample space, not trying to do any fraction math, 1 or more heads would show up here, here, and here, but it would not work here, which means 3 out of the 4 work, which means Jill is wrong. The probability should be of at least 1 head is actually 3 over 4. Okay, but let's talk about why her math didn't work. Okay, when we think about probability of heads on the first one, if we count those from our sample space, there are 2, and 2 out of 4 really is 1/2. If we look at heads on the second one, that is the first one and this one over here, so there really are 2 out of 4, and that really is 1/2. The issue was that this one right here had heads on the first and heads on the second. We have to subtract off the intersection, because as it was with her math, the intersection was counted twice. So I'm going to have you go to your note card and show you what this is on our formula. Okay, so going back here, if we look at the addition counting principle, yes, we can add the probabilities to get the union, but only if they're mutually exclusive events. Because we can have heads happen on the first one and heads happen on the second one at the same time, these go in the group where not mutually exclusive is happening. So you do have to subtract off that intersection if you're going to use the formula. Okay, so be careful of that. Next one is looking at a sample space again, but this time our sample space has a situation where your outcomes are not equally likely. It says we're not doing heads and tails where heads and tails are equally likely. We're going to talk about blood type. And it says 42% of people have type O blood, and we want to look at 2 people at random and check whether they have type O. So when we're looking at the sample space, we could have the 2 people both have O, or we could have one of them has O and one of them doesn't have O. We're not going to split it up into all the different blood types. Then the next one, the first person could have something other than O and the second one had O, or they could both be people with other blood types. So we still have 2 people, or 2 options repeated 4 times here. But we don't necessarily, or 2 repeated 2 times, excuse me, but we don't have them equally likely. If we think about these outcomes, because O is less likely than not O, our least likely is the OO, both of them. And the most likely, because the not O was higher, and you can write this up here, complements again. You can't have O and not O at the same time, so they have to hit 1 or 100%. Then our most likely will be our not O, not O. And then it says, what is the probability that they both have type O? Okay, so this is kind of like what we did last time. If we want to find the probability of OO, we take 0.42. That's the probability of the first person. Then we take it and times 0.42, again, for the second person, to get 17.64%, writing it as they gave it to us. If you wanted to use the actual decimal, you could. Probability is percent or a decimal. And we're really making an assumption that we didn't realize we were making the last class. So when we were talking last class about the multiplication counting principle and some of those strings with replacement, you didn't realize that this math only works because the events that we were looking at last time were actually independent. When we're saying OO, we're saying O and O is happening. That's the intersection, and we can multiply the 2 separate probabilities because the first person having O will not change the likelihood of the second person having O. So we're assuming that the events are independent. And that's a good assumption to make if we're selecting 2 people at random. But on the next part it says, what would happen if the 2 people weren't selected at random if they were in the same family? Okay, for this one, it wouldn't be a good idea to multiply those because if one person has type O blood, that makes the next person in the same family much more likely to share that blood type to also have type O. Okay, so because of genetics, the probabilities will change. either more likely or less likely to have O, based on what ended up happening. All right, last thing here, we're going to talk about some definitions from this chapter again, and we're going to use math symbols to do it because that's what they're using here. We know mutually exclusive means there is no overlap, but mathematically that says that the intersection does not exist, which means the probability of the intersection is 0. Complementary, the same thing is true. There is no overlap. So the intersection's probability is still 0, but it's more specific. There's also a requirement that when you put them together, you hit the whole set. And the probability of the whole set, or the probability of the union then, would have to be 1 if you get everything. Independent, we learned today. That says that the intersection should be equal to the probability of A times the probability of B. And then none would mean none of those patterns are happening, meaning you've checked all of them. Okay, so we're going to go through here, and because all of these requirements use the intersection, we got to make sure we have it first. So on this first one, we're given the union, not the intersection, but we're going to use our math formula, and all we have to do to find the intersection over here is add up the two separate ones and subtract off the third one, subtract off the union. I know it's not set up that way, but you can add over the intersection, subtract over the union, and then it is set up that way. Okay, so with that in mind, you're going to take your 0.4 plus 0.2 equals 0.6, and then you're going to subtract off what you're given. So that means your intersection is 0. Okay, essentially, if you put those together and it matches the union, then there's no overlap. There's nothing that you counted twice. So go ahead and write this down. Intersection is 0. And then we're going to run that through these checks. So intersection is 0. That means A works. The second one, we already checked that part, but we have to check this one. It says the union is 1. Ours wasn't, so it's not part B. And the last one, we want to take A times B and see if it's equal to that intersection. If we take 0.4 times 0.2, we get 0.08. If you want to write it, you can. And that is not equal to 0, so it's not independent. So that's it for number 13. We're going to do the same thing for the next one. You take this plus this is 0.7, subtract off the 0.6, and that gives us 0.1. That tells us our intersection, and then we can run it through each of these. Okay, our intersection is 0.1, which means it cannot be A, and it cannot be B, because those require the intersection to be 0. Then when we go over here, we're going to take A times B and see if it is 0.1. So over here, 0.2 times 0.5 is 0.1, and that does match. So this is C. Pause the video, try 15 and 16 on your own, come back to check. 15 was complementary because the intersection was none, and it hits 1 for the union. This last one already gave you the intersection. If you added them and subtracted this, what you found was the union. Okay, just to clarify, you found the union. But as soon as you know that this intersection is not 0, we don't really care about the union because it cannot be complementary. These were independent. All right? If you have any questions on your homework, please come see me so we can get straightened out.